what you're having with homework or anything, and I'll be glad to show you. And then we can probably more or less do that on Thursday as well. So the reason why I do these kind of lecture things is just because I want to create these videos for you. And then also people just, I don't say it gets me in trouble, but if you don't go over the material, then people can complain and say, well, you didn't go over that. And then I can go back and say, well, here it is. Here's a video of it. This is what we went over. So I know that you can't necessarily keep up with where I'm at right now, because I think probably most of y'all are still in chapter 2 as far as doing the work. But like I said, we should be able to more or less finish up chapter 3 today. And then, like I said, then we can kind of have informal classes next week to kind of lead us into that first test. Anything? Any questions? All right. Well, we looked at 3.1, which is essentially the mean, median, and the mode calculations. You really can't say that mode is a calculation, but it is. Those are all three measures of center. And they're important because they can help us find out and understand about the data set, about where the center of it is at. And then it can be very helpful to help us understand whether the data is proximally symmetric. Or you can even find out about the skewness too from those things. But 3.2, just to kind of recap a little bit, we looked at the idea of the range, which is measures of variation. And I'm going to write that up here. I probably should have done that up here earlier. 3.2 is measures of, I think they call them spread in this book. All right. Well, just to go back and recap that example that we looked at the calculations for the range of San Francisco, highest minus the lowest, and we had a range of 12. If we did something similar in New Orleans, I got that data in the notes. You can calculate the range for that. The range is larger in New Orleans, so that means there's more variation throughout the year. It's more spread out. But the range is not a very useful calculation in statistics. Which is more important is something called the standard deviation. And the good thing about the standard deviation, well, there's a good and a bad about it. The bad part is it's a handful of little calculations you got to do. And the good part is along the way, you get another calculation called the variance. Now, in reality, most of the time, the standard deviation gets done with some kind of technology. And I'm going to key in on two different things here. By the end of this day, I'll kind of show you how to key in and put data into the calculator, and you can get all of the calculations that are in the the third chapter. And then also I'll try to do the same thing with especially if someone's got a homework problem, I can show you how to do it with Excel. Because generally, if you got a large data set, Excel is the best way to do it, because it's easy to make a mistake if you're dealing with a large data set. And truthfully, most data sets are going to be large in real life. They give you all these ones that are just a handful in the homeworks, but generally they're large. And when we say large, we mean greater than 30. All right, so that being said,
Mr. Cruz, do you mind going over one more time approximating the mean? Is that kind of basically the same thing as mean?
Well, here's the thing, okay? If you've got all the original data, then you just put it in, just add them all up and divide by the total number.
Okay.
But okay, let's go back to what you're talking about, though. I'll just go through this example a little bit slower than I did, because why we say it's approximating the mean is because of the fact that we don't have the original data when it's in a hold on a second, let me find it. When it's in a frequency distribution or a histogram, we don't have the original data. All right. So let's just kind of look at it. They break it down into steps here.
Okay.
All right. But the main thing is you. Let me go back and just look at this. This is a frequency distribution. What this is, it just took a sample of 50 people or students and the number of tests that they sent out the day. And what the column all the way to the left, the classes represent is 0 to 49 is the first class. And the class width is 50. Now, that's not 50 for the number of high school students. That's 50 techs. So they keep adding 50 all the way down the left. And then, of course, they go from 0 to 49. Again, that's 50 if you count 0. And then they add 50 and they go all the way down. The reason why we're doing that is those are the classes in which all the values fall. In other words, there were 10 people that sent between 0 and 49 texts. There were 5 people that sent 50 to 99 texts. Then it looks like we're hitting on the big guys here because there were 13 folks that sent between 100 and 149 texts. And then for 150 to 199, there are 11. And then we're starting to come down now. 200 to 249, there were 7 folks. And then 250 to 299 texts, there was 4. So all the data that we have for the 50 students falls in those categories. Now,
I can't hear you if you are talking. Is anybody else doing that?
now what we're going to do to find the rest of the midpoint is just keep adding 25 to all these along on the far left. So 50
Mr.
plus
Cruz?
25 is 75. Mm-hmm.
We couldn't hear you. You just like cut out for a long time.
Oh, really? Like when? Tell me when.
I think the last thing I heard you say was the students, and then you was just going down the row of just explaining each of them of what was the 250 to 299.
Okay, can you hear me now?
Yeah, we can hear you now. It just cut out like right after that.
Well, like I said, I think something funny is going on with the internet. And I think that's why I'm having that issue that I had with the audio. I really think that's what it is now. There's nothing with the computer. So this was happening last night. I was having the video, and actually I can put on my, show you me if you want to. I don't really need it, but. All right, so let me just kind of briefly sum up what I was just saying is, you understand, hopefully from chapter 2, that the frequency distribution
Yes, sir.
gives us just the range of what possible texts are. In other words, there are 10 in that first category, 5 in the next, 13 in the third one, 11 in there, 7 and 4. Now, for each one of those, we don't know what those values were. So we can't possibly calculate the mean. So what we have to do is just an approximation. And what we're going to do is hold on a second. I was just trying to see what the text said. Yeah, it's just that when you're dealing with individual connections and all that, if mine goes out or if yours goes out, it's really hard to say. But anyway, that's what the frequency distribution represents. Now, what we're going to do is, since we don't know what those values are, we're just going to create a midpoint for each one of those. All right. So the midpoint, since the range for each one of those, the class width is 50, we're just going to go halfway to 25. All right.
Now I see how they did that. Okay.
So then 50. So 0 plus 25 is 25. 50 plus 25 is 75. 100 plus 25 is 125, and so forth. So that is the midpoint. So what we're just going to do is just take the middle, and we're essentially going to do an approximation and using that number to represent all 10 of those in there. All right.
Okay.
So now what we're going to do is the things that are important is these numbers here. We know that those add up to 50, but we're going to use that later. But now what we're going to do is multiply these two columns. And every now and then I'm looking up to see if y'all have any questions or if I'm cutting it out. So, all right. So now we just multiply across. 25 times 10 is 250. 75 times 5 is 375. 125 times 13, 1625. 11 times 175 is 1925. 7 times 225 is 1575. And 4 times 275 is 1100. All right. So that's what they call the midpoint times the frequency. Essentially, what that's doing is it's telling us the number of texts that are being sent. Okay.
Okay.
In each category, or it's approximating them. So now we're going to add all of those up. We really only need these two columns now. But if we add all of those of these up, we get 1,600. I'm sorry, 6,000. One second. Let me move that. Anyway, it's 6850. 6,850 is the sum of the column all the way to the right, the midpoint times the frequency. So that right there is where the approximation is at. All right, because since we have the original data, we just kind of got to fudge it and come with an approximate value of 6,000 texts sent. Now, remember, there were 50 students, and that's what these all will add up to. So just like the regular mean, you're going to divide all of the total by the 6,850. I don't know why won't it let me pull that down. Anyway, I'm going to just have to show you on the board. You know what? I guess I must have the whole, because I'm, my computer must have just went off for a second. And again, that's one reason why I like to do two computers. Like I said, it says it's not working on that aspect. So anyway, because I lost my presenter status, I had to grab it back. All right. So the mean is equal to, let me just go ahead and type it out there. divided by frequency, or total frequency. All right. So let me go ahead and just write it out. So we had 60, 8, 50, divided by 50, and you can do the calculation if you want, and then we'll double check. So 6850. So that's 137. So the mean number of texts sent per student is 137. But again, they call it an approximation because you don't really know the true number of texts sent. So I mean that's approximation using the midpoint. All right.
Thank
You heard all that?
I did. Thank you.
Okay, good. All right, so let's go back to talking about that standard deviation. See, everything's acting weird. I just went back and it's like half my stuff is, I think it's just the internet. I don't know. Well, anyway. So let me just go ahead and show you the PowerPoint. All right, so the first thing we're looking at is this kind of wicked looking formula called the population variance. Now, this is, since it's for the population, they use that Greek symbol. That's a sigma. This looks like a 6 that somebody's kind of kicked over. And that's the way I try to draw it, because it's not easy to draw, but if you draw a circle and then just draw that little tail at the top, you can pretty much get it. So that's how you know, can identify us from the population, because it uses that sigma. And there's a 2 up there because that's like an exponent. So sigma squared, and I'll just break down what that is saying. It's, again, the summation, and that's the same kind of summation you use with the mean, where you just add everything up. So xi, and what xi means, it just takes every one of the data values, subtract the mean from it, and then square it and add all those up. And then you're dividing in the same way that you do with the mean by the number of data pieces that you have. All right. Now, this is for population, and there's a slight difference when it comes to doing the sample, and we'll look at that in a little bit. But like I said, it's good to be able to do this on a small data set, but there's no way you can do this on a full data set of doing it by hand. But we'll just look at it. Now, the first thing you got to have is you got to have your mean, no matter whether it's the population or what we're going to see in a bit with the variance. We need to have the mean. So that's the same old calculation that we add up all of those numbers and we divide by 5. Now, for some reason, you can't see them. And let's see if I got it in this other one. I don't know why those things are. Yeah, here we go. Okay, here we go. Now you can see more. All right. So they all add up to 406. Well, that other one had part of it, and this one has the other part. But they all add up to 506. 406 divided by 12. So we got to have that mean. All right. Now I'm going to show you this. I'm going to go back over to the board and do this on that board if the board cooperates. I bet you it's just Canvas acting up. All right. So I'm just going to draw a little table here. They don't quite show you everything they're doing when they're doing it on that slide. So I'm going to show you. Oh. Yeah, everything is just acting weird today. And it was doing that last night too. So that's just kind of to be expected. There's all these people using the internet these days. All right. So what I'm going to do in this first column is I'm going to write out all the, you know what? Save this right here. I'm going to come back and I'm just going to take you through this one, and I'll do the next one like that since it's a shorter data set. I think that'll work a little bit better. So let's go back to this. So I'll just explain it, and then I'll do the next one. It's a little bit smaller. What happened now? All right, because everything's slow. Oh, I see what it's saying. It's saying that something went wrong. Now, one of the things I might try to do this in this class is I've heard that they put Zoom in here. Before it was just a standalone kind of thing, but somehow they, there we go. They've put it in here, so I may try and see if that works better sometime. I'm not going to do it today. All right, so we calculate the mean, and then what we're going to do is we're going to subtract the mean from every one of these values here. All right, and what's going to happen is some of these are going to be negative. So if a value is less than 57.5, it's going to be negative, and you'll see that on the first one. 51 minus 57.5 gives us negative 6.5. 54 minus 57.5 gives us negative 3.5. 55 minus 2.5 gives us 55 minus 57.5 gives us a negative 2.5. 56 minus the 57.5 gives us a negative. Now, this next number is the first one that's larger than that mean. So 58 minus 57.5 is 0.5. So now it's positive. 60 minus 57.5 is 2.5. So we got two of those because it was two 60s. 61 minus the mean is 3.5. 63 minus it is 5.5, and then all of these other ones here up until the last one are all positive. And then we got another one where it starts to get cold again. It's lower than the mean, so we got negative 5.5. Now, that's the first step. Now, I'm not going to show you on this one. Like I said, I'm going to show you on the next one, the smaller data set. But if you were to add all these up right here, you would get 0. And that's always going to happen if you've done everything correctly up to this point. If you calculated your mean correctly and you did your subtractions correctly, all of those will add up to 0. So it's a built-in checkpoint. And like I said, I'm going to show you on the next one. Now, to finish the next step to getting that whole thing that was in the numerator, we got to square each one of those middle rows now. Now it's in the middle row. So the negative 6.5 squared. And this is something you got to remember. When you square a number, it will always be positive. Whether it's a negative number or a positive number, the square is always positive. So negative 6.5 squared is 42.25. Negative 3.5 squared is 12.25. Negative 2.5 squared is 6.25. Negative 1.5 squared is 2.5. So these are all positive. 0.5 times 2.5. And now you'll see, oops, I thought I could select it. I guess I can't. But look at the third column here, the 55, and compare it with the one over here with the 60. Since this was negative 2.5 and that was 2.5, when you square these, they both come out to 6.25. All right. Then we got another 6.25. Then we got the 3.5 squared is another 12.5. Here's a new one altogether. The 5.5 is 30.25, and so forth. Here we got this one and that one are the same when we square them, whether they're negative or positive. And the reason why we're doing this is because the step to take in the standard deviation involves a square number underneath there. All right. But in order to out the
Your mic's going out, Mr. Cruz. Mr. Cruz? Hello?
All right. All right. Sorry about that. I just had to go through the mic check again. I finally got the connection back, the internet, and then. All right. So sorry about that. So let's just go back and I'll just finish explaining this. All right. So as I said, the numerator of this variance calculation is just the sum of all those squares. So that's where the 169 comes from. And then the n is just the total number of pieces of data. Since we're dealing with a population, it's 12. So 169 divided by 12 is 14.83. Now, I'll show you one more thing, because as I said is, you get two calculations for the price of one here, so to speak. All right. Let me show you, give you a little graphic here. I'm gonna have to write it, but I was trying to find it. All right, we're going to look at something in a second called the sample standard deviation. And there's one slight difference. Now, for the population or the sample, the standard deviation is just the square root of the variance. So let's go back and take the square root of that number that we had. And then we're going to show how easy that is to do. So let's go back over here. And we're going to go to the board. And it was what was the value? 14.083. So sigma, and as I said, this is not an easy thing to draw. But it's the square root of the sigma squared. And we know what sigma squared is. It was 14.083. All right. Sorry about that. I said I can't really type out square root sign, so on here. So 14.083 is 3.75. I'm just going to go up one more, 7.753. So as I promised, with the standard deviation, you get a second calculation along the way called the variance. The standard deviation is by far the most important thing. I think the book puts a little bit too much emphasis on asking for the variance, because I don't know what anybody ever does with it. The standard deviation is what's useful, and we'll see why when we come back from our little break in a bit. I'm not going to break just yet, because I want to show you one more example. Now, the one that I want to show you is slightly different, and I showed you a second ago, but I want to show you the formula.
So, Mr. Cruz, when you square the 14.083 .083. You're finding the deviance. That's what we're finding.
Okay, there's several little things in there. When we subtract the mean from each one of the data values, each one of those little ones, whether they're positive or negative, are called the deviations. In other words, that's how far away they are from the mean. The square of them is the square of the deviation. In other words, when we square them and they're all positive, that's called just the square of the deviation. Now, we don't really need to know what those are. It's just that it's a process to get to the whole calculation. All right. Okay. So, but that's what we call those things. The first step is the deviations. The second part is the square of the deviations. And then when we add them all up, it's called the sum of the squares of the deviations. And like I said, the formula looks kind of wicked because it just involves a number of steps. So we're going to look it through another example that's very, very much the same thing. And there's just one slight little bit difference. Go ahead and share back to the PowerPoint. I'm going to just blank out this whole. I just don't understand why it's doing that weird stuff, making everything not fit on the screen. But we'll come back and use that in a second. All right. So let me just share back on the PowerPoint so you can see the formula. But there's another one. The first one we did was called the population standard deviation. This is a sample standard deviation, and there's one slight difference. Now, of course, there's a different symbol for it. For all of the population parameters that are called, they use a Greek symbol. Here, the sample standard deviation is just denoted by the letter S, and so the variance is just S squared. But we're heading towards just having an S. But this is what we've got. So besides that, we're using the term x bar in here, which is the mean for both. It's just the mean for the sample. There's only one difference. Again, I wish I could, but this is a formula, so I can't just select part of it. But there's only one slight little difference. There's the n-1 down there. All right. Now, there's a whole slide over here that explains why we divide by n-1. And you could probably read that. And if you understand it, that's good. You could explain it to me. I'll explain why I think it is. And it's because when you're dealing with a sample, the sample is smaller than the actual population. Now, if depending on how small the sample is, that n-1 is going to make a greater bit of difference. And so it essentially allows us to err on the side of caution when the sample is small. And that's the whole reason for it. Like I said, they give you this whole thing, explanation, and I can read it and I said, I don't understand what that even means. You'll never really need to know why this is. It's just that when you're dealing with a sample, n-1 is important in that denominator. Okay. All right, and then this is another screenshot from well, it's not a screenshot. It's just showing you if you use the calculator, you can get all these calculations, and I'll try to show you that by the end of the day. All right. So let's look at this last example, and we'll take a little break. All right, the sample variance works like this. It has to be done on a sample, of course, and this says a company that manufactures batteries is testing a new type of battery designed for laptop computers. They measure the lifetimes in hours of six batteries, and it's just 6 batteries. It's not all the batteries. The results are 3, 4, 6, 5, 4, 2, and it says find the sample variance of the lifetimes. All right. So they've got the calculation here for the mean right in that slash in the middle. If you add all those numbers and divide by 6, they add up to 24. and 24 divided by 6 is 4. So the mean is 4. And I really wanted to go over this because this one is a little bit less complicated looking. So now I'm going to go back over to the board, and I'm going to go ahead and draw another one here. But I like to use these little tables. They'll help better than I think the examples will show you in the text and on the online stuff, the helps. So like I said, then you have another way you can refer back if you still don't understand. So this first one is just going to be X. So what we're going to do is we're going to put all those 6 values there. Let me see if I can. So 3, 4, 6. 5, 4, 2. All right, I just like to do them vertically like this, just to show you what's happening. And then this is going to be X minus X bar, X minus the mean. And we've already been told that X bar was 4. They calculated it for us, and we could do the same thing if we wanted to, but. So y'all following all right? Holly, you still in there? Okay, thanks, Elizabeth.
I'm here.
All right. So I'm just going to show you the calculation, just so you can see all the little pieces. So we're just going to subtract 4 from every one of these. So this right here, it's -1. Okay, and if you got any questions about what I'm doing here, just let me know, because I'm assuming that this is like pretty obvious, but all I'm doing is subtracting 4, which is the mean, from every one of the pieces of data, all 6 of them. All right, so we got -1, 0, 2, 1, and 2. And now this is what I wanted to show you. Let's just say we want to sum all these up. And that's a summation sign. That's a big sigma. Why don't you add all those 6 numbers up in that second column, not, all the way to the right. What happens when you add up the -1, the 0, the 2, the 1, and the -2? I told you this on the first one, but here I want you to actually see it. What happens when you add all those up?
0.
Yeah, 0. And hopefully this makes a little bit of sense, because the reason why it should make sense is the mean is the numeric middle. Okay? So all of these should add up to 0 if we did the calculations correctly up to this point. I'm going to put a little bit more room on this one. Give us a little bit more room. So that should always happen, no matter what the data set is you're calculating the standard deviation / variance for. All right, now this one is going to be the square. And this is the reason why I'm writing this is what it looks like in formula. All right. So what am I squaring here? So that's x minus x bar, no matter how bad it looks. If you want to see it, go and look at the PowerPoint formula. Just x minus x bar squared. So if we square -1, we get a 1. Remember, these values are always going to be positive. 0 squared. Now these you don't know what they're going to sum up to, but we're going to need all these sums when we do finished. The sum of all these. Another 0 squared. So there's another 4, because that's -2 squared. Now, the sum of these, and again, that's the capital sigma, it just means sum. What happens when you add all these up? 1 and 4 is 5, and there's 6, and another 4 is 10. All right. Let's see. So let's go back over here. I just wanted to show you how all those little intermediate things worked. We'll go back over and now we'll look at the PowerPoint. Now that we've filled in the blank. All right. So as I said, all of those squares end up being 10. And like I said, to me that what they're doing that horizontal way, it's a little bit confusing. That's why I wanted to do it for you vertically and just show you the individual steps. See, you're going to get the -1 squared. The second one is the 0 squared, and the 2 squared, the 1 squared, there's another 0 squared, and then -2 squared. But they all add up to 10. Now, since this is a sample variance, this is the one difference from the population variance standard deviation. We have 6 pieces of data, so we have to subtract 1. And like I said, the explanation why, you can read that, or you can go back and listen, or you can ask me again about why we're using -1. But 6 minus 1 is now 5. 10 divided by 5 is 2. All right. So the variance is 2, but the more important thing is the standard deviation. And as I said, it doesn't matter. This part is exactly the same for both the sample and the population. It's just one last step to take the square root. All right. And so we saw this one already on the first one about the temperatures. The square root of 14.083 was a 3.753. I showed you that. And now the square root of the variance of 2 is 1.414. Now, you probably, like I said, the standard deviation is a bear of a calculation. I mean, if I were going to recommend a way to do this, I would be able to take a small data set like the ones here and do it by hand. But most of the time you can do it with a calculator. And then if you got a large data set, you could use spreadsheet. And then I'll also show you that too. It's real easy in both cases. We'll look at the calculator today. And then if we have time, I'll show you how easy the spreadsheet is to do. Especially if you got a problem that involves data where you can download a data set from chapter 3, send it to me and we can look at that. But we're going to take a little break now and we'll just come back, try to take 10, since we already took about enough of a break with with technical problems. So I'm going to pause this video.
If you're talking, I can't hear you. Mr. Cruz?
All right. So whatever it is that's causing that glitch when I go out for a few seconds, I have to redo my mic. Evidently. All right. So this is the rest of 3.2 then. I don't know. It seemed like this should be in 3.3, but it doesn't really matter. But the empirical rule is just a way to tell when you have approximately symmetric data. You can know what percentage of the data is between 1, 2, or 3 standard deviations. So 1 standard deviation on either side of the mean is approximately 68% of the data. In other words, it's that part that's light blue in the middle of this. That's about 68%, or you could almost say 2/3 of the graph, the entire graph. Approximately 95% of the data will be within 2 standard deviations of the mean. So that goes out to the next darker blue, 95% plus or minus 2 standard deviations. And then when you go out 3, you just get a little bit more, and they say almost all. And when we get to chapter 6, you'll see what almost all is. It's actually 99 point something 7. All right, so hopefully you remember this data that we created the stem and leaf for it. And this was 51 pieces of data, and it's the percentage of older folks over 65 that live in each state, plus the District of Columbia. Now, they created a little histogram for us here, and it's right below the data right there in the middle. And they're going to judge and call that this is approximately symmetric or approximately bell-shaped. All right. It's not skewed to the one side, the hump's in the middle, so we can say that it's approximately normal. Now, what they've done, and like I said, I'm going to try to show you this soon when I get a nice little data set to do it with. But if you were to enter all those 51 into the calculator, and then you hit the var1 stats calculate thing, this gives you everything that's in all of chapter 3. But the only things that we need here are the mean and the standard deviation. All right, the mean and the standard deviation. So the mean is 13.25. A standard deviation is 1.683. Now what we're going to do is just find the percentage of that data there, all those 51 values that are between. Now what gets me is this thing looks perfect. The last night I was doing it on my other, my newer PowerPoint, and I had to move that little graph because it was like chopping off part of the thing. So I just don't know what's going on with this stuff. I'm usually pretty technical savvy, but this is things I can't explain. I'm starting to believe that there's ghosts out there. All right. Now, Here's the way the empirical rule. If we want to find out what percentage of those 51 values are between one standard deviation, well, we can just subtract one standard deviation to the mean, which is 11.57. We can add one standard deviation to the mean, which is 14.93. So what that means is, and they've written them down here on the bottom. I just had to scroll up a bit so you can see it. That 68% of those 51 values are between 11.57 and 14.93. So in other words, I'm not going to go over there and show you exactly which ones they are, but I'm going to do a quick calculation. 0.68 times 51. So 35 of those values, of those 51 values, are probably going to be between those two endpoints. I'll show you on the larger ones because it'll be easier to find them. All right, now, two standard deviations is 2.6827 times 2. So that's 3.3654. So just say 3.4. And if we subtract 3.4 from 13.249, we get just a little bit less than 10, 9.88. And on the upper end, when we add that 3.4, we get 16.61. So that's the endpoints for 95% of the data. All right. Now, remember those three things because I'm going to go back up here. So 19.88 and 16.61. So let's go back up to that data. All right. So it was 9.88, 16.61. All right. On the bottom side or on the left side, there's one here, 8.8. As I remember, that was Alaska. And then 9.0 was Utah. So on the lower side, because all of the other ones are in double digits. So 9.88 was basically, we could almost round it off to 10. And you can see there's only two on here that are less than 10, the 8.1 and the 9.0. Now on the upper end, it was, what was it, 16.61. So on the upper end, there was 17.8, which was Florida. What else is greater than 16.6 or 16.7, we could just say? There aren't any. Everything else is, the next highest one I see is 16.0. So that's three of them that are outside of those two endpoints for two standard deviation. In other words, 3 from 51 is 48. 48 divided by 51 is right on, almost right on the money, 94%. All right. So that just shows you how accurate this empirical rule is. And look, that data, and you can see with the histogram there, it's not very, it doesn't look perfect, but yet once we judge it to be normally distributed, it's more or less going to be accurate. It's not going to be perfect because that's why they say approximately. Then if we go out to 3 standard deviations, I won't go through the calculations because it's just 3 times that standard deviation. That gives us the endpoints of 8.2 and 18.3. 8.2 and 18.3. Now, 18.3 was greater than any of the values out there on that data. But there was one sole value that was lower than 8.2, and it was the 8.1, the Alaska. So two more, when we went out to 3 standard deviations, it swallowed up 2 more in that span. The only one now is 8.1. And so that means that now there are 50 of them that are in that range. So 50 divided by 51. Oops. So that's 98%. So that's the almost all. Just one of them doesn't get inside of there when we go out 3 standard deviations. So that's how you can use the empirical rule and how valuable it is when you know that data is approximately symmetric. Now, just to mention about the Chebychev rule, well, it's not Chebychev rule, it's called inequality. And I'll try to make this a little bit easy to digest. But basically, the Chebychev inequality is not going to be as accurate because when we use the Chebychev's inequality, we either don't know if the data is approximately symmetric or we know it's not. And they give you an example of a data set there that's just all over the place. All over the place. So the empirical rule is not going to work here. But see, it says in that last line, Chebychev's inequality holds for any data set. Any data set. And why? And so this is why it has 2 things to kind of compensate for this. It uses the term at least. All right. It's not approximately. It just says at least. And you almost don't need to worry about this calculation for the most part. I'll just show you how it works. What you just kind of need to remember are these 2 things. They don't deal with 1 standard deviation. They deal with the 2 standard deviations and the 3 standard deviations. And notice, because we don't know the layout of the data, these things are just not as accurate. Okay, for this first one, let me just show you how they get it. The 3/4 or 75%. If you take 1 over 2 squared, you get 2 squared is 4. So 1 minus 1/4 is 3/4. And then same thing for the 3. 1 over 3 squared is 1/9. So 1 minus 1/9 is 8/9, or 89%. So that's where they come from. You can do it for any standard deviation, but generally, you're only going to deal with these 2. So what we can say then is at least 3/4 or 75% of the data are within 2 standard deviation. Notice that it drops down by 20% because when we knew that it was normally distributed, 95% approximately for 2 standard deviations. And for 3 standard deviations, we're going now from almost all to just at least 89%. So that's really all the Chebychev does. And you'll know to use those two things when you see that thing about at least. All right. All right. Any questions about anything? All right. So let's say now we're in 3.3 measure of position. And the reason why I written that on the blackboard, I said, oh no, they didn't have the slide in here to show we were going to 3.3. And they did, because I made sure it was in here. Because like I said, I redid these things. Like I said, I don't know why certain things aren't showing up. All right. Now, measures of position. The first thing that we look at under measure of position is something called the z-score. We know about the sample mean. All right, it's just add them all up and divide by the total. And I'm going to have to replace this one just for visually, because it's just something about the way that it's displaying. I don't understand why they can't have some kind of uniformity on these things.
See, that one that you was just on, that other PowerPoint, the both PowerPoints that you're using, is that what you're meaning, how they're both different? Because that's
no, that's the old one. That's the one that I replaced.
Okay, so you replaced it with this updated one.
Yeah, and like I said, it's just that things are not rendering like they should. I don't get it. Like I said, and it's I don't know what's going on. Man. What is somebody sleeping? Putting people to sleep?
Sorry, that's my dog. No, I'm unmuted. Just so y'all could hear that. I'm sorry.
That's all right. Y'all are a pretty quiet class, but like I said, I was pleased that when I saw that y'all were all tearing up the work. So, okay, there it is. Well, I guess I'm just going to show you with this. And like I said, we're recording, so we got it. I just don't know why. Like I said, yes. All right, this is kind of neat here. I didn't realize it did this. But if I switch back to the other PowerPoint, then it shows this one. It just shows whichever one's active. All right, but this is the z-score calculation. What the z-score calculation is, it's the deviation divided by the standard deviation. I mean, so by the standard deviation, and that gives us the relative position of that piece of data. Is what it is. Because you remember, x minus x bar. Well, in this case, they just call it mu, because we're talking about population, essentially. But this calculation is the same no matter what. So we take that deviation and we divide it by the standard deviation, and we get this thing called a z-score. All right. Boy, this is weird. It's like it's going back to the old stuff, the stuff we just did. I guess we're just going to go back to that other PowerPoint. Yes, it is. I just don't get this. All right. Just a brief word about the z-score. Okay. This one had all these calculations in here, and everything is like out of order. All right. Like I said, we'll just use this old one because it seems to be more stable, at least. All right. So let's try to just use the z-score. Do something. And what we're going to do is we've got some data here that tells us about the mean heights for men and the standard deviation for men in the US. And then they also tell us the mean height for women in the US and the standard deviation of 2.8 inches. Okay. Now, we got those two things because to do a z-score calculation, you have to have those three values. You got to have the mean, you got to have the standard deviation, and you need a piece of data. All right. So they ask us who is taller relative to their gender, a 73-inch tall man or a 68-inch tall woman. like I said, this is one of the things that went fine last night because I mean, this newer PowerPoint had all these calculations in here, but it's jumping back to the stuff that we already did, and it's like it's all jumbled. I just don't know what to say about that. Oh, my God, mic cut out again?
No, I can hear you.
Oh, am I looking at an old one? Oh, okay, that was probably before the break. Yeah, it happened again. Okay. All right, so just, well, if this kind of keeps up, I know what to do. I mean, I got a different way of writing the thing. Like I said, I thought this was all working fine. It might be just something to do with the, I don't know. Gosh. Well, anyway, I'm not going to worry about it. All right, so let's do Z calculations for both of those things. Just kind of those values, we got to take them over here onto the board. And we're going to do the Z score. I'm just going to write the Z formula. We just say XI because it just means it can be for any data value. You can put mu or X bar, it doesn't matter. They're both the same thing for the population. And then the standard deviation. So now let's just say we're going to do the Z score. What was it for the men? It was, we had a 73-inch tall man. And I'm just going to put here Z is 73. Now, this is where you got to remember, you always have to put the number, the data value first. All right. And then we had a mean of 69.4. And I think it was 3.1. And yes, it is. And so what does that come out to at the top? Say 73.
3.6.
Thank you. 3.6, right?
Yes, Rocco.
And then if we divide by 3.1, we get 1.16. Generally, you round your z-scores off to 2. So 1.16. All right. So now let's do the lady. It was 68 inches tall. So I'm just going to put a little 68 here, just so we know which one is which. We could even put 73-inch tall man here and then a woman here, just so we know which is which. So it was 68. But we have to use the mean for the particular data, which in this case it was for women, it's 63.8. And it was 2.8. Yeah. So do this calculation with me. Let's just make sure we can double check. One of the things about statistics and oftentimes just math in general is it's a good idea to have another way to verify your results. I mean, I like the idea that you folks are here and can help me make sure that I'm not making any mistakes. So then 4.2 divided by 2.8 is 1.5. Now, the way the z-scores work, they can be either negative or positive. If they're above the mean, then they're positive. If they're below the mean, they're negative. Now, which one is taller with respect to their gender? Well, it would be the 68-inch tall woman, because their standard deviation, and you can kind of see it from this. If we just kind of look at the graph down here, see on the bottom is the z-scores. So 1.5 would be smack dab in the middle between 1 and 2, like right in here. So it's further to the right, and then the man is 1.16. So that's how the standard deviations work. I mean, the z-scores work. They allow us to tell how many standard deviations a particular value is away from the mean. If it's positive, it's on the right side, meaning that it's greater or a larger piece of data than, the mean. And then on the downside, it's less than the mean. All right. Any questions about that? Because that's probably one of the things I probably ought to put on that. All right. No, 13 things I got on there. There's one more. I don't have 13. Okay, anyway. All right, let me just have a word about what a percentile is. A percentile is just a fancy way of saying percent. So, and really the formula they give you here, I just don't really like it, but I'll kind of explain what this means. This right here is kind of a visual, but a percentile just divides everything into ones. In other words, there's 100 pieces. It's a percentile is sort of like a penny as compared to a dollar. Pennies are percentiles essentially for dollars. There's 100 of them in a dollar. So percentiles and is just percents. Now, to find a percentile is going to be very similar to how you would find a quartile, but basically you just take the percent as a decimal and multiply it by the number of pieces of data you have, and then you if you have a partial value, you just round up. And I'm going to show you here with quartiles, just because that's a little more full. The percentiles are not all that useful, but once you learn how to do it with a percentile, with a quartile, it's real easy to do for a percentile. All right, so let's talk about these quartiles first. Now, remember, the median is the middle of the data set. It's right smack dab in the middle. All right. It's a visual middle. And the second quartile, when you divide the, see, I thought they might have a nice little drawing in here. Yeah, I'll find you one. I'll drop it on the notes, let's say. And the reason why quartiles are important, and I'm going to put this in the notes here, and then I'm going to switch over to the notes. To show you. I don't have a whole lot in chapter 3 because I'm trying to play by the rules. But this right here, this little image is a real important one. Of course, this is getting a little bit too. Let me find another good one. Yeah, this is better. That other one, that you can't see it yet, so I'll explain in a second. All right, so let me project the notes over there. But the first quartile is the equivalent of 25%. So it's like a quarter in either a game, a football game, a basketball game, or a quarter milk. It's a quarter of the whole. And of course, when talking about milk, it's, gallon. What they call it a quart. And then the third quartile is 75 percentile or percent. And then the second quartile is essentially the median. It's 50 percentile. Let me show you this little image in the notes here. I like visual things. But this is kind of how it works visually. You can kind of see right smack, if you look at the mirror point down, what they call the 50th percentile, or that's also the second quartile, which is the same thing as the median. So that's your hinge point for your mirror image. And then 25%, the smallest 25%, and the median are split by the 25th percentile. You can also call it the first quartile, or Q1 is the way you can see it abbreviated. And on the other side of the median and all the way up the highest value, the third quartile splits that. So that graph is split into 4 equal parts, 4 quarters. Okay. So what does this mean? Well, like I said, that new PowerPoint thing, I put some neat stuff in there. I don't know why I can't bring it up. It just looks, I don't know, just a lot of little things here. Because they showed some neat little calculations over there. But I can explain them and do them for you. All right. All right, so to find the quartiles, this is what you do. So we're going to look at some data here. All right, so let's go back over here and rebroadcast back to the PowerPoints. All right, this is a pretty large data set, but it's 45 pieces of data. You could do this either on the calculator or the spreadsheet. If you copy it and paste it, it's easier to do on a spreadsheet. I'm not sure. Working as it should, but back in action. Okay. All right. So so look at this data here. This is 45 pieces of data. You've got 15 in each row, so 3 times 15 is 45. And what we want to do is we're going to compute the quartile, the first and the third quartiles. We'll also find the median, but we know how to do that, but I'll go through it again. Now, in order to find the first and third quartiles, we're going to do it as percentiles, okay? Now, they show you this little formula here, L is equal to P over 100 times point N, because math people have to get extremely like formulaic. But all you're essentially going to do is you're going to find P of 25 is divided by 100 is just 0.25. That's all we're going to do is we're going to take the percentage and calculate it as a decimal. So what I'm going to do is back over here on the board, So Q1 is equal to 0.25 times the number of pieces of data, which is 45. All right. What does that come out to? 0.25 times 45. So we get
11.25.
all right, now, here's where it's a slightly different than the median, okay? All right. You could almost look at this as the median of the first half of the data, but we're doing it as a percentile. And I think the way that they tell you this, like I said, if my good notes were working, since, and so that's, I know what, I'm gonna have to change something. That should be L, not Q. Well, since L is not a whole number, we round, and this is where it's different, up to 12. All right. So I'm going to go back over here and fix that. This is technically what we call the L because it's the position. It's not Q1. All right. So the L of Q1 is equal to 12. Now, what does that mean? In order to find Q1, what we're going to do is we're going to go back over to that ordered data and we're going to find the 12th position. All right. So we're just going to have to count over. We know it's 15. We could kind of go backwards. We go on. Let's just count forward. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm sorry, 9 is 0.49. So Q1, hold on a second. It was 12, not 9. I'm sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What? No. What's going on here? Something strange is happening here. Hold on.
Is it maybe because it says right under the little table, it says there are 42 values? Did you say it was
42? Okay. I'm sorry. You know what? Because this, they changed the data set in the new PowerPoint. Okay. All right.
Somebody said that on the comments too. I'm sorry.
Okay. You're right, Elizabeth. I'm so sorry about that. Like I said, I'm trying to do a all right. So let me go back. So it's 42. Well, I'm glad y'all are paying attention. Makes me feel better. But I did it on in the other class. I did it with the newer ones because the newer ones were working fine. I don't know what they're not working, but anyway. So 42, and then what does that come out to? 42. So I guess what they did is they updated the PowerPoints to for 3 more years. So 10.5. So it's the 11th position now. So the position of Q1 is in the 11th spot. So that means, let's go back over to that data. And so 11th spot, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wait a minute. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11. So 0.67. So you got to count them right. And like I said, I'm going to show you, as soon as we finish this, how to put this in the calculator and do it real quick. And like I said, we could also do it in Excel, but I mean in any kind of a spreadsheet. But I'll show you that next week. Especially if you got a question that comes from the homework, we can just kind of download it rather than type it in, and that'll make it go a lot smoother. But anyway, so let me go back over to the board. So Q1 is 0.67. So now the L of Q3 so now instead of using 0.25, we're going to use 0.75 because the third quartile is in the 75th, is essentially the 75th percentile. All right, so what position is that? And remember, this is, when we calculate this, this is not the Q3. In the same way, when we find the position of the median, you have to go and find it. What you calculate is the position. So 31.5. Bump up to 32. You always got to go up to the next whole number. If it's a whole number, you can keep it there. But if it's got any partial amount, you bump up. So 32nd position. So let's see. Let me rebroadcast this. So let's see. So 12, 1, 2, 3, so it's 13, 30, 26, 27, 28, 29, 30. So Q3 is right there, 5.54. So what that means is that's the number in the data that separates the 0.75 on the bottom. What did I say it was? 5.54. All right. So the median, remember how we did that? Well, we got 42 pieces of data. So there's no middle value. So we got to take the two middle ones. So I'll just kind of go back over and quickly do that. So the median would be in, let's see if I can find it real quick. That other data set with 45 is real easy because it's right smack dab in the middle. But this one, we got to find the two middle ones and then add them. All right, so here are the two, well, I got to broadcast it. Yeah. It's taking a sweet time. All right, so the two middle ones are right here, the 2.84 and the 3.06. If you always wanted to verify why, go back and look at what we talked about in the for the median. If the data set is even, like this one is, we got to go to the two middle values and then add them up and divide by 2. So 3.06 and then 2.84 and then divided by 2, we get 2.95. Yeah. All right. So now I'm just going to write on here that the Q2, and like I said, if you got any questions, refer back to 3.1. And I mean, I don't mind showing you, but I'm just for lack of time. So Q2 is equal to the median is equal to, I forgot what it was now, 2.95. All right, now what are these useful for? Well, we can do something that's called a 5-number summary. So we've got the ones that we had to calculate, the Q1, the Q3, and the Q2. All right, so let's go back over and look at this slide. And they've got over here, this is what the 5-number summary is called. And we'll talk about why this is important a little. But the 5-number summary is made up of the first quartile, the median, and the third quartile. And then you also use the minimum and the maximum, which are pretty easy to find because if you got your data sorted. So this is it for this 42 pieces of data. The median was 0, the maximum was 13.68, and then the Q1, the median, or Q2, and Q3. So that's how we find the 5-number summary. Now, I told you I was going to show you how to do this on the calculator because these things are really hard to do by hand when you start getting into large data sets. And this one is considered large because this one's over 30. 30 is like the magic number. All right, so let's see if I can bring that calculator here. I know I installed it somewhere. There it is. All right, so let me, the good thing about this online, that online calculator, that one, let me broadcast it for you, is that it can be made bigger than the actual calculator is, and as big as your screen is. All right, so hopefully I can do this without having to refer back to my notes, but and if you need help installing this, let me know. I've got the instructions somewhere in there, but all right, so what we got to do is, and this is probably the hardest part, is putting all the values in. And this is why I think Excel or some kind of spreadsheet is really the most valuable tool for doing statistics. And as a matter of fact, a lot of the problems that have data sets for the standard deviations and other things allows you to be able to download that data. And like I said, is once you do that, I mean, that's the hard part. And that's the really hard part on the calculator. But next watch. So what we want to do if we want to enter data is we want to do second and stat. All right. Oops. Did I mess up? Let's see. I may have to look this up again. I thought it was second and stat, and maybe it's. All right, hold on a second. Let me do a quick search. Oh, it's stat enter. Okay. So you don't need the second. You hit stat and you hit enter. All right. I can only make this as big as my screen. I wish I could make it bigger on for you folks, but you can probably, after you, if you want to come back and look at the recording, you can blow it up. Now, what we got to do is the hard part, which is the hard part with a calculator, is put all these values in. And I'm going to put those 42 values in there. All right. And all you got to do is just type in and hit enter. So I'm just typing in all of those. And this is the tedious part, because if you make a mistake, oops, what happened? I must have hit something on it. Like I said, this is the tedious part. So 0.14, enter. And when you're like, got a lot on your head, you're trying to rush, you see how I made a mistake real easy there. This is why being able to download into a spreadsheet is by far the best way to do this, because you don't have to worry about the accuracy of the data. Because here, when you put it into the calculator, the accuracy of the data is only as accurate as you putting it in. So you got to double check it every time you go across, put one in. And the good thing about this, though, is when you get it in there, you're going to get every calculation from the entire chapter. And the same thing with Excel. You got to do a little bit to set it up. There's a way to do them really easy by doing individual calculations. But if you got one little thing you got to adjust first, it essentially does the same thing that this does. It'll give you all of them at one pop. All right. 1/3 of the way there. I mean, 2/3 of the way there. But I'm trying not to rush because I don't want to. I want to double check as I go because one little mistake is going to throw everything off. Can you still hear me?
Yes, I can hear you.
Okay, I heard something strange. I thought maybe it disconnected again. It might have been somebody on the other end. It just sounded like something went out. All right, so we're just about done here. You can see that this is the hard part. We're just going to punch a couple of buttons in a second, and we're going to have all these things. All right. Now, where they show us this thing. All right, it's voice. All right. So I think this is. I forgot from what it was. I gotta have to go back and. I certainly don't want to mess all this up. Just using the calculator is not something I do very often, but I want to show you. 1 second. I think I got the instructions here somewhere. Okay, so okay, here we go. All right, so you hit stat again. So both times you hit stat. But now instead of editing again, which is what you did the first time, you go over to calc. Here we go. Calc. And then you hit enter, 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 and you got everything you'll ever need here. At the top is the mean. They call it X bar because they don't know whether this is a population or a mean, but the calculations are the same, so it doesn't matter. The next two you don't really need here. You could use them in chapter 11, but I don't see why you would need them there. So sometimes you may need these. What's important is the last two here, and you got to know the difference between these two. All right. Now, this is the population standard deviation and the sample standard deviation. They give you both because they don't know whether this is a population or a sample. All right. They don't know that. So they give you both. So in this case, we're talking about a population because it's all the years, like the rainfall. So 3.57, but we don't really need that for any of these calculations here. I was just showing you that you can get the standard deviations from this. You can get the means from it. So you can see you get the standard deviations, 2 standard deviations and the mean for 1 pop. Now to see the rest of the stuff, you hit the scroll down, and we're almost finished. And you got to go down to several to get to the next page because you were at 41. Oops, it looks like I missed one putting it in, see? But anyway, so they're not going to match. But anyway, I must have skipped one. But anyway, see what they give you? They give you the minimum, and that was 0. They give you the maximum on the bottom, which was the 13.68. And they give you the Q1, the Q3, and the medium. So you get everything in this whole chapter in one calculation, but you just got to do what I did there, not do what I did there, which was miss one of the data items. I didn't want to keep you all on here if we didn't have to. So if you got any questions, let me know. I'll stick around here and answer it. I'll even try to fix that if you want me to, so you can see that it looks exactly like, let me show you. It'll look exactly like what they have over here on this screen print of that. How did it get real big like that? I should have just done this. I didn't think about that. That looks, well, it's still not that much bigger. I thought I made it bigger, but why in the world is my thing bigger? Anyway, I'm going to get out of here.
I just wanted to tell you that I do have an appointment. It was for 1:35, so I'm going to have to go.
Well, let's go. That's fine. I didn't mean to keep you. I just wanted to do that calculation to show you that you could do it.
I wanted to stay and see it, but she's calling me right now on the virtual thing.
That's fine. Like I said, guys, I'm going to save this, and then you can see